Good morning. We've got the usual suspects here. So, did I successfully get the homework assignment posted? That's something I haven't checked from the student side view yet.
Yeah.
It's up. Okay, good. Any questions on that so far?
Been on the
It says-
theoretical ones, and so far they're pretty good.
Say that again, Lily.
Oh, I've been working on the, I guess, the problems 1 through 4, and so far they're fine.
Okay, Nolan, what did you say? Nolan, you were coming through at the same time as Lily.
I was wondering, when it says, I believe it's question 4 that says, the speed cannot exceed the speed of light. So is there an upper limit on the energy and momentum?
Oh, shoot, we haven't gotten to energy and momentum yet. So
Okay.
maybe for now, yeah, you could read ahead a little bit if you want. But otherwise, we'll talk about that probably next week is when we're going to get around to that stuff, because this is already Wednesday.
Okay. The assignment's due on Friday, though, is the only
Yeah,
problem.
I know. Let me look here and see. Let's see. Chapter 37, I think. Yeah. Length, Lorentz Transforms. I think I may be able to introduce momentum and energy a little bit tomorrow. And then I'll put off the Doppler effect for electromagnetic waves till after those two. So, yeah, we'll be able to talk about that tomorrow, I think. So you should be able to answer it by then anyway, or after that. Okay, well, let's jump into the Lorentzian transforms here today and see what they look like. And I'll start off with kind of restating the Galilean transformations that we looked at yesterday. And this seems like a sort of stilted, ooh, I just noticed that parts of my drawing migrated on my notes. Oh well, but this will seem like a stilted way to address these things, but an unrealistic situation, but maybe not as much as you might think. So, and yesterday I drew these two different coordinate systems, one of which was moving with respect to the other one. And this will be the S coordinate system, and this is the S prime coordinate system. It has coordinates y prime and x prime, and this has coordinates y and x. And an important thing is that, the separation between the two is ut, where u is the velocity of coordinate s prime with respect to s. And the Galilean transformations, or something that we'll assume here, is that at t prime equals 0, we'll have that x prime equals x, or x equals x prime, y prime equals y, that's supposed to be a y, and if we had z's, we'd have z is equal to z prime as well. Now, the transformations at later times end up looking like x is going to equal x plus or x prime, excuse me, plus ut, y equals y prime, z equals z prime, and at all times t is equal to t prime. And these all end up looking the same. One thing that would be different is, or in the primed system, we could say that x prime is going to equal x minus ut. So if we've got some coordinate x on a position in space here, in the x system, it would be ut plus x prime. This would be x prime, y prime. And in the x prime system, the coordinate of this is just going to be x prime, which is the x coordinate minus the ut. So no real surprises with that. But what are these going to look like in a primed system? And they're going to look different. Alfred Lorentz came up with these before Einstein published his paper on special relativity. And these are all the Galilean transformations. And they're things that we could get kind of from just reasoning arithmetically. We wouldn't have to use anything really special to get it. But then the Lorentz transformations are going to be different. So and for the Lorentz transformations, we're going to get a bunch of new stuff mixed in, and I don't expect you to know where these things are going to come from, except that Lorentz was monkeying around with trying to explain some observational data. And so that's my version of gamma. This will look a little bit different than it did in the other ones. So it'll be gamma times x prime plus ut prime. So this is letting us figure out the x coordinate of something when we know the x prime coordinate, but we also need to know the t prime coordinate as well. And then we've got gamma in there, which we never saw before. Y is just going to equal y prime, so that's no big deal. T, though, is not going to be the same between the two coordinate systems. And it's going to be gamma times t prime plus u x prime over c squared, which is just bizarre. And then z equals z prime. So now this is like a single measurement of time, not a delta t in prime. And so it's not just the gamma t prime, it's going to be something else. So that's going one direction. Going the other direction, this is going from the primed system into unprimed coordinates. Going the other direction, you would end up with x prime is going to equal gamma times x minus, excuse me, ut. Let's see, these we don't have to rewrite, they're going to work all the time. But the t prime, the time in the primed coordinate system, is going to be gamma times, that's not a very good gamma, times t minus ux over c squared. So these two look very similar, except one has a minus sign, one has a plus sign. And these are unprimed, those are primed. So it's not exactly like you can solve these things for each other, although if you worked with these two equations together, you could solve the one of them for x prime and the other one for t prime. So It's a little bit more work, but I can restate the thing. Y prime is equal to Y and Z prime is equal to Z. We're not going to do anything where we have to worry about Z prime very much. We might do one example with Y, but probably not. Now, what about the velocity transformations? Those are going to be kind of fun to play around with. How would we get to something like that? Well, what we do is we take the X prime and T prime equations that I've got here and convert them into differentials, dx prime and dt prime. So to get to those, I'd look, dx prime is going to equal, gamma is just something that depends on the relative velocity between the two coordinate systems, and it's going to be the same in both coordinate systems, and it's not going to change. We're assuming constant velocity here, so we won't have anything there, but we would have dx minus u dt is what dx prime is going to equal, and then dt prime is going to equal gamma dt minus u over c squared dx. So, and I think you probably did some differentials in calculus. I'm not sure. I thought I remembered doing that in calculus, although I remember doing them a lot more when I took a class in special relativity, so maybe that's not quite the case. So then, dx prime dt prime, what's that going to look like? So, which is what we would call v sub x prime. Or v prime sub x. I'm not sure what I want to call that. Yeah, just v sub x prime, I guess, would work for that. Well, it's just going to be the ratio of those two things. The gammas are going to drop out, and I'll have dx minus u dt divided by dt minus u over c squared dx, and I can multiply the top and the bottom of this thing by dt, and I would get dx, or by 1 over dt, dx over dt minus u on top, and then on the bottom I would get 1 minus u over c squared times dx dt. So this is something that's going to let me transform from a velocity in the x direction in the unprimed system into the primed system. And so dx dt is just going to be v sub x, no prime on that one, minus u. And on the bottom I would have 1 minus u v sub x divided by c squared. Let's see, interesting thing is that the numerator of this expression is what you would get in the Galilean transformation. The denominator is something completely new. And so we'll see what happens when we start doing calculations with these things. And then we could actually solve this for v sub x prime and go the other direction, but I'll maybe let you try that for yourself, or maybe we'll need it in a problem and we'll do it when we get there. But these are the new transformations, the Lorentz transformations going from one system to the other. And let's try it out on some examples, and I'll probably have to be switching back and forth between the example and the equations just to keep them fresh in our minds here. So we'll see how those work. Okay, so suppose the S prime system is moving to the right at 0.55c, So that would be u. That's the thing we've used as the relative velocity between the two systems. Two events occur in this system, that would be the S prime system, which an observer in the S prime system judges to be simultaneous. One event occurs at x prime equals 0, the other at x prime equals 4,500 meters. So if I was to make a sketch of this, I'll just do it in the x prime system here. And I guess I don't need to have a ruler for this. Whoops. I don't want another axis over here. I'll just continue this thing out. Here's where one of the events occurs. And this is going to be y prime. This will be x prime headed out in that direction. And then the other event is going to happen out here at 4,500 meters. And an observer here judges that they're simultaneous. Well, maybe that observer is going to have to be halfway between the two or something like that. We can worry about that later. But at any rate, let's see. This observer says t prime is 0 here. And so whoever claims that these things are simultaneously starts their clock at that instant. Now, when are each of those events going to occur to an observer in the S system and the time interval between the two things? So in this case, we're just going to be using our transformations that'll take us from the primed coordinate system into the unprimed coordinate system. So we can try and figure those out. Well, let's see. Event 1, which we can call this one, and we'll call this one event 2. Both of those happen at t prime is equal to 0. So our x or t position for event 1, yeah, it's the t's I want, when they occur and the time interval between the two and which occurs first. Okay, I'll just call it t sub 1. That's going to equal gamma times t prime is 0 plus ux prime over c squared. Well, let's see. X prime is 0, so it'll be u times 0 over c squared, and I get zeros for this. So this event that was happening at time 0 in the primed coordinate system, this is S prime, will also happen at time 0. Well, that kind of makes sense because we set these things up so that at t equals t prime equals 0, x prime is equal to, or excuse me, well, I didn't write it down for this one, but the two systems coincide at t equals 0, and that's what all our setups depended on. Okay, so event 2, when is that going to happen? We'll have t2 is going to equal gamma times t prime, which is 0, plus u x prime is 4,500 meters divided by c squared. So that's going to be non-zero. Okay, we're going to have to actually calculate gamma now because I'm going to need it. So anyway, gamma is 1 over the square root of 1 minus 0.55 squared. And that's 1 minus beta squared, and beta is 0.55 when the speed is 0.55 c. So we can see how that comes out. Okay, and it's not a whole lot different from 1, but it's 1.20 to Oh, let's see. I guess we've only got 2 sig figs, so I can call it 1.2 is what I can keep on there. So that'll work out okay. Anyway, that T2 is going to equal 1.2, our gamma value. And then all I've got inside the parentheses is going to be U, which is 0.55. Did I copy that down right? I think I did. Yeah. 0.55 C times 4,500 meters. And I divide that by C squared. Okay, well, let's see. This C will take care of one of those. That C is just 3.00 times 10 to the 8th meters per second. If I divide meters by meters per second, I'll get seconds. So I get 9.9, actually, times 10 to the minus 6 seconds, or 9.9 microseconds for that. So what's the time interval between the two events? Well, it's going to be 9.9 microseconds. And this observer would say that the observer in S would say that the event at 0 occurs first and the event here occurs later. Now, let's see, is that going to make sense for this to be the case? Let's see, the trailing event occurs sooner. I'm thinking, let's see. Imagine that the observer who sees these things in the S system is right here, and this system is moving along like this. It's going to take time for the light from these events to arrive. Well, anyway, they disagree about the simultaneity, excuse me. Let's leave that be for the time being here, but they would say that the event 1 occurs first. Now, if the S prime system is moving to the left at 0.55 C, I'm crying out for a better picture than what I've got here. So I want to do these things so that I'm going to kind of shadow one with the other. So here's the S system, and here's the S prime system. And I want to go back to that first event here, where we have something happening here, and we have something happening 4,500 meters out along there. So if an observer in S prime judges that these two events are simultaneous, one way they could do that is if they're exactly halfway between the two events. And so that's what's going on. But the observer in S is going to disagree about the simultaneity of these things. And I think you could think of the observer in S as moving to the left with respect to S prime. And if they're moving to the left, and they're also midway between these two events, but the positions are going to be different. Anyway, if they're moving to the left in there, they're going to run into the light from this event before the light from this event catches up to them. And that's why we get the backwards event here. But then the second part asks, what if the S prime system is moving to the left at 0.55 C? And so S prime is actually going in that direction at speed u. What's that going to do to our equations? Well, what it's going to do is put a minus sign on this one and a minus sign on this one. Anything that's got the 0.55 c in it is going to have a minus sign. So for part B, event 1 is still going to have T1 equaling 0 because I had zeros all around in this particular for event 1. This is the one that took place at the origin. But event 2, that's the one where we had, oh, let's see. Yeah, this is T2 is going to be gamma times 0 for the first term in there, which was the T prime. I think it's still T prime. Yeah. Minus the U, the 0.55 C, or yeah, I should stick it in there, 0.55 C, 4,500 meters. The numbers end up being exactly the same as the last time. The only difference is the minus sign, and that's a meter on there. So you end up with T2 happening at minus 9.9 microseconds for that one. So if the observer is going to the left, they'll agree, yeah, that first event happened at time 0, but the second event happened before it. So not only do they disagree about simultaneity, they disagree about the order of events depending on the direction that the S prime system happens to be going with respect to the S. So that's different. So I guess we have to throw away simultaneity. The only way two observers would agree about simultaneity is if both events happened at the same place, but that pretty much turns it into a single event if it happens at the same time in the same place in space. So that's not going to help. All right, well, let's see what we can get. An observer in frame S prime is moving to the right in the positive x direction at a speed u equals 0.600 c away from a stationary observer in frame S. The observer in S prime measures the speed v sub x prime of a particle moving to the right away from her. What speed v sub x does an observer in S measure for the particle if well, we're going to be going from speeds measuring in x prime into speeds measured in x. And we've got formulas for going one direction, but we don't have them for the other direction. We could repeat what we did with differentials here and see what comes of that. I suspect that the fact that these ones had minus signs and these ones have plus signs mean we'll get something like the same formulas with plus signs. Or something else you could do is to solve this equation for v sub x instead. And I'm going to do that just for the heck of it. You can play with the differentials if you want to, but what if I multiply out from underneath by v sub x, or this denominator, and see what I get? I would get v sub x prime minus u v sub x prime over c squared is going to equal the numerator v sub x minus u. And then let's see, it's the v sub x's that I want. So if I bring this over here and add the u over there, I would get v sub x prime plus u is going to equal v sub x plus u v sub x prime over c squared. And if I factor the v sub x out of here, I would get 1 plus u v sub x prime over c squared. And then if I solve for v sub x, I'll get the kind of intuitive guess I had. V sub x will end up equaling v sub x, whoops, that's supposed to be v sub x prime plus u divided by 1 plus u v sub x prime over c squared. So yeah, the only difference is I replace the v sub x with v sub x prime in both cases and replace the minus signs with plus signs. So that was encouraging. Already worked out. Now let's try this problem here and see if we can make sense of it. So observer in frame S prime is moving to the right at this speed, away from a station observer in frame S prime. And then the S prime observer measures the speed v sub x of a particle moving to the right away from her. What speed v sub x does the observer in S measure for the particle if A, v sub x prime equals 0.400 c, v sub x prime is that, and da 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 da. Well, we can just plug these in. V sub x will equal, I'm going to copy down the formula here, v sub x prime plus u. Now remember, the numerator is what we would get if there was no special relativity stuff. So, and then 1 plus u v sub x prime over c squared. Okay, u is 0.600 c, v sub x prime is 0.400 c. I forgot the 0 on the 1, but that's all right. Okay, if I add those two together, I get the speed of light. And so this observer in v sub x would claim it should be going at the speed of light if they didn't know about relativity, but relativity does exist. And so we have to divide by this denominator down here. So 0.600 c times 0.400 c divided by c squared. Well, c times c is c squared. It's going to be 1 plus 0.6 times 0.4 is 0.24. So I'll get 1.000 c divided by 1.24. And so it's going to be less than the speed of light by, actually this looks like about 4/5 to me, but not quite. And I think we can keep 3 sig figs. Yeah, it's 0.8 or yeah, 0.807 c. Okay, so it's not going at the speed of light. Well, these other ones, if you look at those, this would make the Galilean prediction, which is the numerator, more than the speed of light. So let's see what happens to those things. We'll have v sub x. I'm just going to go straight to the numbers here. V sub x prime is 0.900 c plus 0.400 c. And on the bottom, I know the c's are going to divide out. I'll have 1 plus.
Wait, shouldn't it be 0.600 c?
Oops, yes, it should. Yeah, I was copying down the wrong speed. Yep. Anyway, but down here we'd have 0.9 times 0.600, which is going to be 0.540. And so I'll get 1.500 c on top, and the uncertainty stays in the thousandths place. But here, this is an exact 1.500 4. I guess I would have had 4 significant figures on this because of the addition. So this was 0.8065. I wasn't watching carefully. So 1.5 divided by 1.54, each good to 3 sig figs, and I get 0.9740 C. So not such a big difference this time, but still it was enough to rob this thing. Well, actually it is a big difference. The Galilean prediction was 1.5 times the speed of light. This says, nope, you're not quite going the speed of light, only 97.40% of the speed of light. And then this next one, C, they're even closer together. We've got 0.990 C. Well, let's see, 0.990 plus 0.600 is going to give me, well, I better write it down. Then on the bottom, I'll have one, I can't do this one in my head, 0.600 C times 0.990 C divided by C squared. Oh, I guess it would have just been those numbers. That's what I was starting on. So 1.590 on top and 1.594. Let's see. Trying to think. Yeah, actually, I have more sig figs than that on the bottom. Oh, well, I've only got 4 on top. So and I would get 0.9975 C. Now, you can kind of imagine, as long as we keep U at 0.600 C, what I can do is tag additional 9s onto this speed that's measured in the prime coordinate system, and it'll get this thing closer and closer to 1.6. So it next term up would be 1.599 C and then 1.5999 C. But this thing on the bottom is also going to keep growing gradually, and it always stays just a little bit above this one. And so you can get closer and closer to the speed of light, but never exceed it. So that's kind of a neat thing to look at those 3 examples there. And in every case, the numerator is the Galilean prediction, but the denominator ends up shrinking that Galilean prediction by just enough to keep it under the speed of light all the time. So yeah, there's kind of a maximum speed of things. Okay, here's a kind of a weird problem, but we could have done this yesterday, actually. A moving rod is observed by someone who sees it as a moving object to have a length of 2.00 meters, and it makes an angle of 30 degrees with respect to the direction of motion. So you'd see this thing going by you, and it's got a speed of 0.995 C, which is pretty good length. Okay. Now, what is the proper length of the rod? Well, one thing that's not going to change is the length along this motion here, which we could call y if we want to, or L sub y, the length in the y direction. It's going to be, let's see, this divided by those 2 meters, is going to be the sine of 30 degrees. And I think we can do this in our heads. So Ly is just going to be 1.00 meters because sine of 30 is 1/2. But that's not the proper length of the rod. That's just the proper length of this thing. And we could call this L sub y prime if we want to. It'll be, we can imagine ourselves as being in a primed reference system that's moving past this place where the rod is at rest. And then we could call this dimension here L sub x as measured in our coordinate system. But moving lengths appear shortened along the direction of motion. So L sub x prime, excuse me, is going to equal L sub x divided by gamma. And that's the factor that it's shrunk by. So in the rest frame of this thing, it's not going to be shortened in this direction. And so it'll have a longer L sub x there. And for figuring out the proper length of it, we have to put ourselves in the rest frame of that rod. So L sub x is going to equal gamma L sub x prime. Well, L sub x prime divided by 2 meters is the cosine of 30 degrees. So L sub x prime will equal, and then we'll be able to figure out that other thing. 2 cosine of 30. Should be able to do this not quite in my head. My calculator is going to give me a square root of 3 or something. It is, yeah. But we don't have that many significant figures. 1.73, I think, yeah. So in the unprimed coordinate system, oh, I have to figure out gamma. Gamma is 1 over the square root of, it's always 1 minus beta squared. Beta is the fraction of the speed of light something is going, and in this case, it's going to be 0.995. So 1 minus 0.995 squared. And that should be a fairly good-sized gamma. Well, oh, it is. Yeah, it's actually 10.0 to 3 significant figures. So L sub x is going to equal 10.0 times that 1.00 meters, or 10.0 meters. Okay, so the proper length of the rod, L, is going to equal the square root of L sub x squared plus L sub y squared, which is the 10 meters squared plus Ly is going to be the same as Ly prime plus 1 meter squared. So which is going to be, when it's 10 times as long as in the other direction, looks like 10.1 meters is what it ends up with. And then the orientation angle in the rod's rest frame, well, we're going to have 1.00 meters here and 10.0 meters here. So this will be theta in the thing's rest frame. And it's going to be the inverse tangent of 1 divided by 10. .00 divided by 10.0. And looks like 57.1 degrees. Wait, 5.71 degrees. Excuse me. Can't read. Well, anyway, there's kind of a neat thing about how the orientation can change so much depending on it. But that's a really high speed. Alas, it would happen so fast we wouldn't have time to have it register on our eyes. Unless it was a whole lot bigger than just a few meters long. Okay, here's one that's maybe a little bit more realistic and something that we can actually observe things like this. A quasar is something called a quasi-stellar object. That's why they got that name. Seemed to me in the 1960s and 70s, there was a TV brand or model called a Quasar, if I remember right. Long history of turning things into, or scientific terms into product names. Anyway, I'm surprised they haven't called a Quasar that, or a car a Quasar yet, but maybe they have. I just haven't been paying attention. Anyway, a jet of material ejected from the quasar towards the Earth moves at a speed of 0.55 c relative to the quasar. Find the speed of the ejected material relative to the Earth. Well, let's do a little picture here. Here's Earth. Here's the quasar. And the quasar is moving away at 0.87 c. Let's see, seems to me the quasars got that name because when they studied this is related to the Doppler effect for light, but you can kind of understand it. When an object that's emitting light is moving away from us, the light wavelengths are lengthened. So we actually get a lower frequency of light coming from it, like you would with a lower frequency of sound if we were studying sound. But the way that they tell that that's the case is that we look at the spectra of objects, and if we looked at some part of the electromagnetic spectrum, we'd see a particular patterns that show up. And one that shows up is there's a place in the electromagnetic spectrum for things that are at rest with respect to us. And it's called the sodium doublet. There are two spectral lines that are emitted by sodium, and they're both just about 589 nanometers in wavelength, with just a little bit of variation, and I can't remember exactly what the variation is. It's like 0.2 nanometers or something like that. But when we study the light from astronomical sources, what we see, if the thing is moving away from us rapidly, we see some of the same patterns of light, like we'll see this pair of sodium spectral lines get shifted toward longer wavelengths. And this is longer lambda, longer or increasing in this direction. So by measuring the amount of shift in there, you can determine the speed at which the object is moving away from you. And we've been doing this with stars and galaxies and stuff like that for a long time. But in the 1960s, they discovered these things called quasars. And what they would find with the quasars was the spectral lines are shifted by so far that they didn't even recognize the spectral lines anymore. They would be focusing in on a fairly narrow part of the spectrum when they were looking at those spectral lines. But if the pair of sodium lines got shifted too far, you'd end up with having a hard time, and you're focusing on one little part of the spectrum. That spectral line by itself isn't going to tell you much because you don't know what it's due to. And so everything gets shifted to such longer wavelengths. And that's what it was with the quasars. And they called them quasi-stellar objects because they had absorption lines like stars do, except the absorption lines were shifted so far that they didn't understand how that could be the case until they actually realized that they were looking at the same spectral lines, just shifted so far that the object must be going a significant chunk of the speed of light. So that's where the history of the quasars came from. Now, do we have time to do this problem still? Maybe. We want the V sub x, but in this case, we've got this stuff that's jetting out of here at 0.55 c. So we'll have that the speed of this quasar with respect to Earth, which is what we want to use as our moving coordinate system, it's going to be 0.87 c, but the V sub x prime in this case is going to be negative. It's going back in that direction. So this time we don't have additive things going on. So it's going to be minus 0.55 c. And so when we calculate the relative speed here, the V sub x, that would be the speed of this jet of material with respect to Earth. Oops. Well, it's always V sub x prime plus u divided by 1 plus u V sub x prime over c squared. But in this case, the V sub x prime is negative. And so our numerator will end up being 0.87 c minus 0.55 c. And our denominator is 1 minus 0.87 c times 0.55 c. And I've already taken the minus sign from that 0.55 c and put it in front, and then divided by c squared. So we can real quick get this one. And we'll do a few more problems with this tomorrow, and then I'll introduce the idea of relativistic momentum and energy, so we can deal with that one question on the homework. Let's see, 1 minus okay, in this case, I end up with 0.61 c for the speed of that stuff. Non-relativistically, you'd expect this to be about 0.32 c, but when we put in the relativistic correction, we actually end up with a greater speed in this case. So okay, we'll stop there and do some more with this stuff tomorrow. But any questions on those? They're kind of fun. You have to practice a few of them to get the hang of setting them up, but they are doable. Just have to be careful with how you set those things up. Okay, I'll turn you loose, and I'm going to have to run out to school today to gather some data for the lab that I want you to do. So this afternoon I'll be out there, and then I'll have to figure out a way to get it to you, and I'll record something for presenting what I want you to do in the lab. I guess that'd probably be the best thing.